Here we'll talk about the equilibrium of nucleophilic addition reactions, and we'll discuss the reaction that was covered in the previous video. So in the aldehyde and ketone 6 video, we take a aldehyde or a ketone. In this example, we used an aldehyde. We added water with an acid, so an acidic solution, and we form a gem diol. So an OH group is added to the carbonyl carbon. This reaction is reversible, and the reversibility of the reaction, or the equilibrium of the reaction, depends on the structure of the aldehyde or ketone. So moving on to this current video, the equilibrium depends on aldehyde or ketone structure. Whatever molecule is involved in the reaction, an aldehyde or a ketone, the structure of that molecule is what influences the equilibrium of nucleophilic addition. So for that specific reaction that was covered in the previous video, we'll look at the equilibrium rates, the KEQ, not the rates, but the KEQ value for the reaction where we're adding water, forming a gem diol to a few different aldehydes and ketones. So generally the reaction is we have two R groups bonded to the carbonyl carbon. So if the R groups are both carbons, we have a ketone. If one of them, at least one of them, is a hydrogen, it's an aldehyde. We add water and some acid is present in solution. We have an equilibrium reaction where we are forming the gem diol. So we still have the carbonyl carbon bonded to both R groups, and the carbonyl oxygen becomes an OH group, and another OH group is added to that carbon. How that specifically happens is covered in the previous video. So the mechanism for this reaction is in the previous video. So using this as our kind of model of what reaction is occurring, let's look at the KEQ values for a few different aldehydes. So formaldehyde, where we just have both R groups are hydrogens, the KEQ for this reaction is 2.2 times 10 to the third. So relatively large KEQ. That means that the concentration of products is higher than the concentration of reactants, so the equilibrium lies to the right. KEQ is greater than 1. If we have acetaldehyde, where we have one of the R groups is a CH3, but we still have an aldehyde, so we still have a hydrogen bonded to that carbonyl carbon. The KEQ here is 1.0. So a magnitude of 10 to the power of 2 change between the KEQ with formaldehyde, where we have 2 hydrogens, and acetaldehyde, where now we have a CH3 group bonded to that carbonyl carbon. Let's look at a couple more here. If we change the methyl group to an isopropyl group, the KEQ doesn't change very much. It's very close to the acetaldehyde. Benzenal has a KEQ of 8.3 times 10 to the negative third. So now we're decreasing by another power of 3, a much lower KEQ, concentration of reactants will be higher than concentration of products. And then if we have a chlorine bonded there, so now we have added electronegative group, we have a very high KEQ. So let's look at all of these and think about the pattern here and use the mechanism to reason through what's going on. So remember, in aldehydes and ketones, we have a distribution of electron density. The carbonyl carbon is electron poor, and the nucleophile present in solution will add to the carbonyl carbon. The carbonyl carbon, being electron poor, partial positive charge, is what causes the reaction to move forward, and what is attracted to the nucleophile that has electrons to donate to the carbon. So the more electron poor that carbon is, the better electrophile it is. Now remember, from our electrophilic aromatic substitution unit, we talked about which substituent groups are electron donating or electron withdrawing. The CH3 group, the isopropyl group, the phenyl group, these are all electron donating substituents. Those are on our list for electron donating substituents. If we have an electron donating substituent providing electron density to the carbonyl carbon, now that carbonyl carbon is not quite as electron poor as it might be, for example, in formaldehyde, where there's no electron donating group. And then if we look at our last example, where we add now into the molecule a highly electronegative atom, chlorine, that's pulling electron density away from the carbonyl carbon in that molecule. So that causes the KEQ to be high. Let's also look at some examples of ketones and the KEQ. So let me zoom in a little bit here. So we first looked at formaldehyde. Let's look at acetone, the simplest ketone, comparing to the simplest aldehyde. If we're comparing to the simplest aldehyde, formaldehyde, to acetone, acetone now has two electron donating groups. The methyl groups are electron donating, so we expect the KEQ to be lower than the KEQ for formaldehyde, and that is the case. The KEQ is 1.4 times 10 to the -3. So a pretty large magnitude lower than the KEQ with formaldehyde, because we have these two electron donating groups, the methyl groups. Then we'll compare with a phenyl ring. So if we have the acetophenone molecule comparing to the aldehyde that's present here. Acetophenone, very similar to the aldehyde shown on the left, except it's a ketone. We have a CH3 group. We have another electron donating group in the ketone, the methyl, and so that has a KEQ, which we would expect to be lower than the aldehyde, and that is in fact the case, 6.6 times 10 to the -6 here. Again, because of that CH3 electron donating group. And then let's compare with this last one. We have a chlorine. And instead of an aldehyde, we have a ketone, so a CH3 group here. We do have an electronegative element, chlorine, pulling electron density away from that carbonyl carbon, which causes nucleophilic addition to happen quicker, for equilibrium to lie to the right, which is still the case when we have the ketone with the methyl group, but the KEQ is still lower than the aldehyde version of this molecule because of that electron donating effect of the methyl group there. So with this table, these are some example KEQ values to help us understand the effect of electron donating and electron withdrawing substituents on nucleophilic addition reactions. Let's look at some key trends here. So just kind of summarizing what's shown in the table, and we can apply these trends to other molecules that are not part of this table here. So the nucleophilic addition, we'll just simplify to addition, in general is more favorable for aldehydes than it is for ketones. That's because all ketones have some carbon group that the aldehyde does not, because aldehydes always have a hydrogen bonded to the carbonyl carbon. So that carbon group in the ketone is electron donating. If we have an electronegative group, like chlorine, near the carbonyl carbon, like this last example, the last two examples here, that makes addition more favorable. And then the opposite, if we have an electron donating group near the carbonyl carbon, that makes addition less favorable. Now, just a note here, all of these KEQ values, I wouldn't expect you to know these values, but I would expect you to be able to compare the KEQ between two molecules. So I would expect you to be able to say that the KEQ for formaldehyde is higher than the KEQ for acetone because of the electron donating groups.